Okay, so law of sines only, SOHCAHTOA only works in triangles that have hypotenuses, so therefore it's only for right triangles. So then we get into a situation, well, what if the triangle that I'm dealing with is non-right? Okay, like this triangle here in front of us. Okay, not a right triangle. I still need to solve for angle measurements and solve for distances like we did in right triangles. How do I go about doing that? Okay, so I'm going to walk you through kind of the progression of what happens here. And we're going to derive the law of sines. So I'm going to call this triangle A, B, C. The traditional thing to do when we call this triangle ABC is to call this side opposite A, we call it lowercase a. This one opposite C, we call it lowercase c. And the one opposite B, obviously lowercase b. Okay? That's the traditional way of labeling triangle side measurements or segments based off of how we name the angles, right? Does that make sense? So if I use like capital D, capital E, capital F, then I'd use lowercase d, lowercase e, lowercase f, right? As the opposite sides. So that's just a common practice there. What I want to do to be able to solve a triangle that is a non-right triangle is I actually have to introduce right triangles. Okay? We should know from geometry that from that point right there, point A, to this segment right there, how many lines go from A perpendicular to BC? One. One and only one. Of the infinite lines that or segments that go from A to BC, there is one and only one that is perpendicular. I'm going to draw that one. You guys remember what you call that? Well, okay, we're going to label it H. Okay, but what was it? What's the vocabulary word for that type of segment that goes from a vertex perpendicular to a line containing the opposite side? It's an altitude. Okay? Now, we could do this from A to BC, but there's an altitude that exists maybe there. Does that make sense? And there's another one that would exist there. Okay? So those are all altitudes of this triangle. We're going to look at that one right here, the solid one. Does anyone know what this point would have been called right there, the intersection of altitudes? Remember that from geometry? Say again? That's the ortho center. Good. All right, so we're going to look at that H. What did I do? I just created two triangles, right? What kind of triangles are those two triangles now? Right triangles. So a triangle, I'm going to call this triangle number 1, triangle number 2. Okay? Inside triangle number 1, I can now use SOHCAHTOA, right? Okay? Now here's the thing. I want to talk about the angles of the blue triangle while working on the inside kind of small triangle number 1. Okay? So this angle right here, I don't have a way of naming that based off of angles A, B, and C. Does that make sense? So I'm not going to talk about that angle. I don't have a way of naming this angle down here based off of just A, B, and C. Okay? So I'm not going to do that. Because when I look at a normal problem for the law of sines, I'm not going to draw this line in. Okay? And I'm not going to try to decipher how big that angle there is or how big this angle here. Obviously, that's going to be a 90-degree angle. But what I can talk about is that angle right there, right? Angle B it's an angle of the overall triangle, but at the same time, it's a full angle, a complete angle in triangle number 1, right? Okay. Now what I want to do is talk about the sides that I have in triangle number 1. I know that I have H's complete distance, right? And I have C's complete distance. I don't know what this little distance here is. It's smaller than A, but I don't know how big it is, right? Okay. So what is H and C? H is what compared to B? What side is it? Opposite. And C is hypotenuse. So can't I say sine of B is equal to opposite over hypotenuse? That kind of makes sense? Okay. Now, for the exact same logic, or with the exact same logic, I'm going to look at triangle number 2. Now, the full complete angle in triangle number 2, that is also a full complete angle in the entire blue triangle, is angle C, right? Could I say sine of angle C is equal to H, I don't know why I put that line there, is equal to H over B. Does that make sense to everybody? Okay. That red formula and that blue formula, what do they both have in it? They both have H. Let's solve both those for H. So the red one would be C sine of B is equal to H. And this one over here, I'm going to write this way. Multiply both sides by B, I'd get H equals B sine of C, correct? This H right here in the red formula or equation, is that the same as that H? It was this altitude, right? So can I do, just kind of give you a visual here. Can I do this? Kind of move this equation over here. Those H's were the same, right? So I have C sine of B equals H, but H is equal to B sine of C. Can I just kind of do this? Substitution, basically, right? Okay. That's the law of sines. Okay. However, it's not in a real kind of maybe useful way of remembering what it is. Okay. So what we do is we take that equation C sine of B equals B sine of C, and we divide both sides by C. And you can do this all in one step or two steps. I'm going to do it in two steps. I divide both sides by C. It gives me sine of B is equal to B sine of C over C. We like this, the sine of C over C, because their C's are the same letter, right? And they're opposite. This one's an angle. This one's a segment opposite. I don't like this B being right here. How can I get rid of that B? Divide both sides by that B, right? And that's going to go away there. So now I get sine of B over B is equal to sine of C over C. And now you see that's the way that we traditionally present the law of sines. And it's easy to remember. It's sine of an angle divided by the segment that is described by the exact same letter that your angle was being described by. And they're opposite one another in the picture. Okay. Now you might be asking, well, where's sine of A come in? Well, what happens with sine of A is that we do this. This set of triangles gives me sine of B over B equals sine of C over C. What would happen is we would draw that altitude. We'd call that H. And now do you see it? That would give me eventually the ability to talk about this angle A and this angle C here. So what I'd end up doing, going through, is I would go through this entire process again, but I would end up at a station once I've done this entire process where I have sine of C over C equals sine of A over A as well. So I've got sine of B over B equals sine of C over C, and then I have sine of C over C equals sine of A over A, and putting those together with the transitive property, I get this extended proportion. Okay. Now, so they always show it to you in a textbook, this extended proportion, but you never will go through the algebra with an extended proportion. So I don't care if you remember as these three or you just use two of them and know that when I'm using law of sines, I have to take those parts. I have to know three of those four parts. I have to know two angles and a side length, or I need to know two side lengths and an angle. And then I can fill that stuff into that proportion. Is that okay? So I'm going to do an example of this. But what happens, guys, is this formula allows us to, essentially what we're doing is we're using SOHCAHTOA, but it's circumventing, the SOHCAHTOA is all of this process right here, correct? All of this stuff all the way through here, which we don't want to do every single time that we come across a non-right triangle, because we get a lot of those. So the law of sines allows us to get through that work a little bit quicker. Okay. I don't remember. I probably should. It's probably in the videos. I know it's in your textbook, but you guys remember the orientations of parts like side, angle, 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 side. We talk about those in geometry. There is a series of like ASA, AAS, that kind of thing that you can look at and say, I know that if it's ASA, I have to use law of sines. If it's side, 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 I have to use law of cosines, and that kind of thing. You can remember those, okay? And if you want to do that, do a quick Google search and say, which orientations of parts do I need to have law of sines? Write them down and memorize them. I'm not going to do that, okay? As we go through the next couple of days, I think we're going to see enough of them, and we'll get to, you'll hear me say, oh, this is all three sides, we're going to use law of cosines, because we see enough of them, and we develop that pattern, recognize that's what it's got to be. But, I've been doing this since I was your age, and I haven't remembered those things, and we could still complete it, okay? But the way that I do it, I'm not saying it's the right way, is what I try to do is I try to use law of sines. Every single time I come across a problem that is a non-right triangle, I try to use the law of sines. And if I can fill in the proportion, those four parts, those four numerators and denominators, I fill those in, and I have one leftover variable, I know law of sines was adequate, right? It works. If I have two leftover variables, law of sines doesn't work, so what will work? Law of cosines, which we'll talk about tomorrow. Okay, so that's kind of the process that I go through, and a lot of times that's you're not going to be wasting time by doing that. It's a very, very quick kind of recognition type thing. Okay, so I'm not going to redraw that triangle again, but we've got this triangle here with angle A, B, and distance C. Okay, so A was 75, B, let's say it was 60, and C is at 340. Okay. So what I'm going to try to do here is I'm going to try to take, I know I've got a law of sines formula that says I'm going to take the sine of something over something equals the sine of something else over something else. But what is nice is that these two things are opposite, right? These two things are opposite. Okay? So, and what goes in we call this the argument. Okay? If you watch the videos in 5.2, 5.3, I talked about that. When we're talking about sine, cosine, tangent, secant, cosecant, cotangent, sine inverse, cosine inverse, secant inverse, all those functions that deal with trigonometric ratios, in the parentheses, that object is called the argument. Okay? This argument has to be an angle. Okay, so it has to be 75 or it has to be 60. But then opposite that has to be a known distance. Well, if I put 75 in here, opposite that would be A, right? If I put 60 in here, because that's my other angle, opposite it would be B, right? In that situation right there, how many variables do I have left over? 2. That's a problem, right? Okay, so that might make me think, well, I got to use law of cosine. But there are some things that they're implying a angle that you actually do know here. If you know two angles, don't you automatically know the third? Okay, so what's angle C up there? 45, right? So what I'm going to do, instead of using 75 in A and 60 in B, I'm going to use 45, because opposite 45 is 340, right? So there I filled in that complete ratio, and I don't have any variables there. Now I'll pick maybe this 60, sine of 60, and then what's opposite 60? B. How many variables do you have left over here now? You have one variable left over. Okay? Now, there's something that I want to let you grab your calculator and all that kind of stuff, but eventually we should be able to do this problem without any use of a calculator. Okay? Because you should be able to get an exact answer here. Okay? But with proportions like this, you cross multiply, right? So B sine of 45 is equal to 340 sine of 60. And then B is going to be equal to 340 sine of 60 over sine of 45. Is that okay? Okay. Now you're going to grab your calculator. I'll let you do this with your calculator right now. If you're going to use your TI 8384, just make sure that you understand that the angles that I'm dealing with are in what measurement? Degrees. Okay? So I need to go to mode before I, and this is something I got to pay attention to on every single problem that we do from here on out to the end of the year. Before you start any problem with your calculator, hit the mode button and make sure that it is in the right measurement. Okay, whether radian or degree. Here it's degrees. Okay, so that is good. Now I'm going to go 340 sine of 60. And we'll divide that then by sine of 45. And it gives me that number right there. So that is the value of B. Okay. Now, those of you that are in physics, you've heard about the unit circle, right? Okay, with it's got radical 2 over 2, radical 3 over 2, and 1/2 on a lot. Okay, and those are paired up with angles of 30, 45, and 60. What I'm going to do, and we did a little bit of this with the reference angle stuff in section, I think it was 5.2, 5.3. I'm going to solve this problem a little bit differently at this stage right here. Okay, instead of grabbing my calculator, I'm going to write that I know that the sine of 60, radical 3 over 2. So you get 340 times radical 3 over 2. I know sine of 45, radical 2 over 2. And I know my algebra says that those 2's are going to cancel out. Okay? That makes sense, everybody? So those 2's cancel out. So I'm going to have essentially 340 radical 3 over radical 2. I'm going to rationalize that, so I'm going to make radical 2 times radical 2. It's going to be 2 on the bottom. It's going to be radical 6 up top. What's going to happen with those 340 and that radical, or that 2? Those are going to cancel, gives me 170, right? That's the exact answer. That's the best answer. And if I type that into my calculator, 170 radical 6, give me the same number. Okay. The benefit of that, though, the 170 radical 6, is that I can be exact now up to any decimal place that I want to, right? Okay. With doing the calculator 340 sine of 60 over sine of 45, and it spits back 416.41325663, I have to round that somewhere, right? And once I round that, I am no longer have an accurate answer, right? Okay. Which is kind of problematic for us sometimes, because the next thing in this problem we have to do, what value have we not solved for? We have not solved for A. Okay. When I want to solve for A, I'm going to use the law of sines again. Let's think about our options. If B, we just found B to equal 416.413. Okay. If I want to go through and I want to solve for A, okay, I now have this side here that I could use. Does that make sense? Okay. So I could say maybe sine of 60 is equal to, or sine of 60 over 416.413 is equal to maybe sine of 75 over A. Does that make sense, everybody? But what kind of number was that right there? What did we do to it? We rounded it. We rounded that to the thousandths place, right? So I know for sure that my A probably isn't going to be accurate out to the thousandths place. Okay, maybe the hundredths place I'll be okay. But thousandths place I'm probably going to be not accurate. What could I do?
Well, either leave it in the 170 radical 6 or just use your given values.
Okay, so using the given values I think is probably the approach that most people are going to use, because we have three ratios that we could use, right? These three things are all equal. Sine of 60 over 416, sine of 75 over A, and sine of 45, this is 340, over 340. So I could use those, and that's what Derek is saying. Those were my given values. Those I know to be exact, right? So I know that when I go through and I solve for A, it will be as accurate as possible. Okay, it will be an exact answer. Now we'll have to round it because sine of 75 right now we don't have really a way of, I think it's like radical 6 minus radical 2 over 4, something like that. So that proportion right there is better than that one. Does that make sense? Because of this rounded value. Now, to make them equally good, now in either of these, I don't have any rounding, right? So it doesn't matter then which one I use. I'm going to go ahead and use this one on the right because it's a little bit easier. Sine of 75 over A equals sine of 45 over 340. Cross multiply, and then divide. We'll do this all at the same time. So we get A is equal to 340 sine of 75 over sine of 45. And again, make sure your degrees or your modes in degrees. Plug that in. I'm good to go. Is that okay? The one thing I need you guys to understand is that when you have essentially this multiplier up here, you saw me when I put on my TIA 384, I put parentheses around it, right? It's not necessary, okay? But I put those in there because at some point, what if this 340 was down here? Do parentheses need to be around that now? Yes, okay? So whenever I'm working with these things and I've got multiple operations in the numerator and multiple operations or multiple operations in the denominator, I'm going to put them in parentheses just to be safe, okay? And now I'm not going to go through that. I'm not going to calculate it out and type that in, but that should give you the value for A. All right? Does that make sense? So that's a traditional law of signs question, okay? Now, you can, based on just the information they give you, be asked to find an angle measurement instead. So you might solve, you might have like sine of B over, like, let's just say 340 is equal to sine of 30 over 210. I don't even know if that will work to give me an angle or distances that makes sense for a triangle. But let's say I end up with that proportion. My variable is now the capital B, right? I have to be able to pull that capital B out by using my inverse trig function, sine inverse, okay? And that's going to spit back then an angle measurement to me instead of what we've been talking about in regards to the last question, distances. And we'll see that here kind of worked out with what we call the ambiguous case, okay? Ambiguous, what's ambiguous mean? Okay, not defined. I think that's a pretty good way of saying it, okay? I'm not 100% sure, right? Okay, let's say, this would be a stretch, but let's say Tyler has a friend, okay? And that friend's name is Pat. Do you know whether Pat's a man or a woman? No, it's left open to interpretation, right? It's not been, based on that name, it's not been defined for us. We're not 100% sure, okay? That's what's happening in the ambiguous case. We're not sure, based off the information they give us, whether we have 0 triangles, 1 triangle, or 2 triangles, okay? So we have to go through that process. Now, when we have to do more work, okay, I think that's a pain in the butt, right? Okay, doing extra work, pain in the butt, pain in the butt. You're going to hear me say this all the time with these types of questions. And the reason I take that phrase, pain in the butt, is because it's only going, the ambiguous case only exists for this orientation of parts. And I would not traditionally write it this way, okay? But does that help me visualize that this is a pain in the butt type question? And then when I have angle side side, because it's a pain in the butt, it's more work. I got to do extra. Does that make sense? On the final, because it'll be, 2-3 months from now that we get the final and we see this as like question 3, and it's worth maybe 8 to 10 points, and we go through it and we solve, we get the first triangle, and we go on to the next one. And we didn't recognize this was an ASS situation, which is a pain in the butt, and I got to do extra work. You don't do that extra work, you're only going to get half credit for that question. Does that make sense? And I get that all the time with this. So we have to be able to pay attention to that. And when we talk about these parts, guys, and traditionally, like side angle side, back to geometry, that meant the angle was stuck between two known sides, right? So that'd be like, if I was talking about side angle side, that'd be like putting the 45 right there. Ignore it down here. And now you've got a side, the angle stuck between, and then another side, right? But when I go angle side side, the angle is now not stuck between two sides. We call it the non-included angle, okay? So you got two sides, and then an angle that is not between them. And that's what we got going on here, right? Okay. Now let's kind of walk through a picture of what's really going on here with the angle side side. What's going to happen with this one, I believe, that the 7 radical 2, if you were to evaluate that, I think it's about 9.9-ish. Okay, so let me take that side to be 9.9. And we had a 45-degree angle. And the other side was 7, right? Actually, that was the 9.9. Get that one. And it matters which side's 7, which one's 9.9. But when I do this, all that I really know, guys, is that right there. I know that I'm going to have a ray, because it's got to be 45, right? So I know that ray exists, and I know that this one exists here. But this is 9.9 everywhere, right? No matter where I rotate it, I have to be able to rotate that out so that it does indeed intersect this dotted line that is being created by this side of this angle. Okay? So when I rotate up there, that would be the one triangle that I'm interested in here. Does that make sense, everybody? What I need to make sure doesn't happen is that I cannot rotate this red X to where it would intersect this dotted line a second time. Okay? So if I rotate that red X, you see here, it does not do that, right? Okay? Let me kind of manipulate the distances here a little bit to see if we could get that to occur. So there, you see, I get one. I intersect with this dimension of 5.4. Is that third or that second side? I guess we leave that triangle there, correct? But if I rotate, I intersect there again, and you see that you now get that triangle, which is now an obtuse triangle, correct? Does that make sense to everybody? So there you get two solutions, and we have to be able to define and talk about those two triangles. Now it's really easy, to do that. You just got to remember that this case is existing. If I look at the angles created here, now I'm gonna, because the rounding is kind of messy here with, I'm not 100% sure if I zoom in whether that's not really intersecting, right? So that's kind of the problem that I have showing you this right now. So I'm going to fix that by doing the rounding or messing with the rounding. Let's go here, rounding, 1 decimal place. All right. Can you guys see those numbers a little better? All right, so if I go there, let's say if that's the one triangle. I'm going to look at that angle there. So that's the angle, that's 66.9. That is the angle that we're going to find with maybe that information up there using the law of sines right away. Okay? So 66.9. The second angle for the second triangle is going to be maybe that one there. 66.9 and 113.1. How do those relate to one another? They add up to 180. They're supplementary, right? Okay? So that is how we check to see whether we're going to have two solutions. We essentially look at, so I'm going to go back to that 66.9 one, and I'm going to actually put, not that angle, that green angle. Okay? Now the rounding is a little messed up here, but those two angles, supplementary, right? They form this linear pair. Well, when I come over here, do you see how those two angles have switched spots? Okay, and that's the ambiguous case. Okay, the fact that we could be talking about that triangle there, or we could be talking about that triangle there. Okay, and the check to this is just simply being able to take the angles that we currently have after doing one iteration of the law of sines. Check the angles that you have and see if you can create a second triangle with the angle supplement. Okay, so we'll go through this process. All right, so this triangle here has those dimensions. It says solve triangle ABC. When it says solve a triangle, it means find all 6 parts. Okay. Now, whether we have time to do all 6 parts for both triangles, I don't know, but we'll at least discuss it a little bit. Right now, I'm going to look at this stuff right here, and I'm going to say laws. It's not a right triangle, so I'm going to try law of sines. So I've got that and that, right? Those are opposite angles and distances, so I can say sine of 45 over 7 radical 2 is equal to, now, if that's what I'm using there for that first ratio, what other value do I have to use in my second ratio? I have to use 7. 7 is a side length. It's a distance, so it's got to be there, right? Okay. And opposite it would be sine of b. So this is one of those situations that we're solving for the angle instead of solving for the distance. Some people, you might see occasionally this formula. A sine of A equals B over sine of B. Is that the same thing? Yes, okay. When I have a proportion, the reciprocal of that proportion is still true. So let's walk through this. Let's multiply both sides by 7. So it's going to give me that, right? What's going to happen to those 7s on the left-hand side? Cancel out. So you're left with that. So you could, at this stage, if we're going to try to get B out of here, what you would do is you would take the sine inverse of both sides. And what you're going to end up with would be something like this, sine inverse of sine of 45 divided by radical 2 is equal to B. Does that make sense? And you could type that in your calculator if you're going to use your calculator. Okay? What I'm going to suggest is to try to start doing is that every time you guys see a 30, 45, or 60 in your angles, is try to avoid using your calculator. Sine of 45, anybody know what sine of 45 is? Radical 2 over 2. Radical 2 over 2 divided by radical 2 is 1/2. So now the question is, what angle measurement will always spit back a ratio of 1/2 for the sine? 30 degrees. Okay? If that went completely over your head, don't really concern yourself too much with it right now. We'll get to chapter 6, and we're going to drill that, and you'll know that by heart. Basically, what chapter 5's purpose is to kind of give you insight that when we go to chapter 6 and we start using the unit circle approach, the unit circle approach is developed from what you have already known from geometry and algebra 2, which is the stuff that's being presented in chapter 5. So we're going to go basically all through reference angles and all that kind of stuff again in chapter 6, but using a different approach, which is a little bit more efficient than the triangle approach, but is developed because of the triangles. So we get this angle here to be 30 degrees. All right. Now, I haven't solved the triangle yet because there's still a missing segment down here, right? What we could do now is we could say sine of 30 over 7 would be that angle and that angle. is equal to sine of, now, do I know this angle here? What is it? 105. Okay, over, I don't know this, so I'll call it lowercase c. And I could have also used sine of 45 over 7 radical 2 here, right? But I wanted to avoid using the radical. So I'm going to cross multiply again. I'll get sine of 30 times c is equal to 7 sine of 105. And I divide both sides by sine of 30, right? 7 sine 105 divided by, essentially sine of 30 is just 1/2. So, but I don't know what sine of 105 is. It's probably, it's another one of those or radical 6 minus radical 2 or 4 or something like that. So in that case, when I don't have essentially a multiple of 30, 60 or 45, I'm going to grab my calculator. So finding c would be 7 sine of 105 divided by sine of 30. 13.52. 13.52 would be that side there. Okay. Now, if I wanted to really do this stuff without using the law of sines, guys, I would have to introduce that distance right there. You know, I had to find h. And then I would have to find that distance right there. Does that make sense, using SOHCAHTOA? And then I would have to use SOHCAHTOA again in this triangle on the right to find that distance. Right? Does that make sense? Once I found those two distances, what would I do with them to find A to B? Add them together, right? Do you see how the law of sines kind of incorporates all that, but does it instantly for you? Okay. Maybe this might have been an approach that we used in geometry. I think we did like a question with a crater hit Mars, and we talked about if there's a probe over the top of the crater, how far is that kind of the diameter of that crater? We would use that approach right there. The law of sines is a lot quicker. Okay, so that is one solution. We have a triangle that has a 30-degree angle, a 105-degree angle, a 45-degree angle, 7 radical 2, and what did this end up being? 13.52. Okay, that is one triangle solution. Okay, if I were to, because this is angle side side, this is the potential for having multiple solutions, right? It's the ambiguous case. Okay, you have 0 solutions, 1 solution, or 2 solutions. We know right now for certain we have 1 solution, correct? Can I have 2 solutions? No. So the question, how do I figure that out? This angle right here that we found, we take that angle, let's call it alpha. We'll take 180 minus alpha and see what that number is. Okay? And we'll see if that number then fits with the rest of the information in the triangle. So what would be 180 minus 30? 150. So if I put 150 in here, with the known information for the rest of this triangle, that's really the only other thing that we knew so far, right? Will that angle and that angle go together inside a triangle? No. Okay? So we blow the triangle up based on the triangle angle sum theorem, so we don't have 2 solutions. We have 1 and only 1 solution. Does that make sense? Okay? If that, let's say we go through here and let's say this angle here was like 100. Okay? If that was 100, we'd have room for this angle here, correct? Okay? What would be the supplement to 100? 80. So if I put 80 there, with those 2 angles, do I have room for a third angle? So that would be the situation where we have 2 triangles. Okay? So I believe I've got one of those here. Let's see if we can get through at least recognizing that the case is existing. So that's the question. Let me do it this way. I've got a triangle already drawn here. And this, Control V. All right, so let's say we've got that information. Let's call this angle A 43.1. Your pictures don't have to be accurate, but don't make them stupid looking. Don't say that, if it's 43.1 degrees, don't make it look like a 110 degree angle, right? Make sense? So this would be 186.2. Now, it doesn't matter what you choose to be B. I'll call that capital B. This will be lowercase b, 248.6. Obviously, that would be C and lowercase c. So right now, given the information, that there and that there are opposite known given parts, right? So let's say the sine of 43.1 over 186.2. Okay, now what angle would be the most appropriate to solve for here, given the defined values? Angle B, right? Because that's the only angle that I know the opposite side for. If I chose sine of C, I'd have capital C here in my argument, and I have lowercase c here in my denominator, and that would be two variables. If I go sine of capital B over 248.6, I should be able to solve that. One variable, capital B. So I'm going to get 248.6 sine of 43.1 over 186.2 equals sine of B, right? How do I get that B out? Sine inverse. And that will just give me just B. So, we go sine. Okay. Something I haven't mentioned to you. If I'm going to use it, I don't like coming down here and hitting the function key and then finding sine inverse. Does anybody know the old world way of saying sine inverse? Arcsine. ARCSIN. Okay? Does the exact same thing. I go 248.6 times sine of 43.1. I'll divide that by 186.2. So if you see there, it gives me 65.8188. 65.8188. And that was angle B. 65.8188. Okay? So here's the question. Can we figure out what C is? We can find out what measurement and angle C is, right? Take those two out together, subtract from 1A gives me angle C. Could you then use the information, because you got 5 parts of that triangle, could you use that information with law of sines then to find segment C? Absolutely. And then you would solve that one triangle with that one solution, right? Okay. But if I look at that 65.8188 number, and I subtract that from 180, 180 minus 65.8188. Does anybody know what that gives me?
114.18.
114.18 approximately. Okay. So this was the first solution, but I could also have 114.18. So that 114.18 along with the 43.1, does that violate the triangle angle sum theorem yet? No, so you got remaining degrees that can go into angle C, right? 22.7. Okay? And now you have 3 angles for a second triangle. You have 2 distances for that second triangle, which are going to be 186.2 and 248.6. And you use law of sines again to find the third C value, right? The third segment. Does that kind of make sense? Do you see how the ambiguous case, it's really doing the same thing over and over and over again? But it's a pain in the butt because you got to do it over and over and over again. Right? And you always got to check it. So when you're doing the law of sines, law of cosines, guys, the law of sines is the only one that has the ambiguous case. It's only going to occur with ASS. Okay? So as you're doing these, whenever the law of sines pops up or you write that proportion on your page, look to see if the parts that you're using are ASS. And if it is, then you got to go to the ambiguous case. If it's not, you don't. You know it's going to be one solution. Does That work? I think it will still be beneficial for you to keep watching those videos under 5.5. Like I said, I'm gonna open up that assignment till Wednesday. Let's do Wednesday night. That work? And I'm gonna give, if anybody try to finish that.
Interruption, just a reminder that at the bell, juniors, you should report directly to the auditorium for your junior class meeting when the bell rings. Again, juniors to the auditorium for your class meeting as soon as the bell rings. Thank you.
If you finish that 5.5 hastily because of the delays and cancellations last week or whatever, I'm going to give some similar exercises on that so you can go back through it and actually do them kind of coherently.